So welcome to the video lecture series on theory of computation. In the last class we have discussed about mathematical preliminaries, and we'll be continuing with the same concept today. So today we'll be learning about what is meant by a Cartesian product. Cartesian product. So what is meant by Cartesian product? So when there is two sets, say for example I have A equal to 1 comma 2 and B equal to 3 comma 4, and I should try the combination, that is one should combine with 3 and one should be combined with 4, and similarly 2 should do the same as what 1 does. So when I write it A into B, so the first combination is 1 comma 3, then the second combination is 1 comma 4, and now you should take the second element of the first set. So you take 2 comma 3 and then 2 comma 4. So this is called as a Cartesian product. So when you want to define it mathematically, so you can define like this. So A into B is equal to cardinality of A and cardinality of B. So this is the mathematical definition for Cartesian product. And we'll go to the next topic called as what is meant by subsets here. Subsets. For example, I can say that A is a subset of B if and only if every element of A exists in set B. So that means I can write like this: A equal to 1 comma 2 and B is equal to 1 comma 2. That means here I can say that A is a subset of B because every element of A 1 comma 2 exists in B. So you can directly write like this. So A is a subset of B. But if you want to say the proper subset, what is meant by proper subset? You can say that a set A is a proper subset of B if all the elements in A exist in B, but B has some elements more than A. Say for example, I can write that A is a proper subset. So proper subset can be written like this: A is a proper set of B if only if every element of A exists in B and B has some more elements than A. So how will you define an example for this? Now I have that A equal to 1 comma 2, and let us assume that B I have 3 comma 4 and 1 comma 2. I can say that 1 comma 2 already exists in B and A has only 1 comma 2. So we can say that A is a proper subset of B. So A is a proper subset of B. Okay, so how will you define it mathematically? So a subset, we can say that A is a subset of B when you can say that A is a subset of B if every element A of A belongs to B. Element of A belongs to B, and we can say that A is not equal to B. So this is the case for mathematically defining a subset here, a proper subset. So we can define that a proper subset can be defined as A is a proper subset of B if and only if A is a subset of B and we can say that A is not equal to B. So this is the proper mathematical definition for this. And the next concept is we'll be learning about disjoint sets. Disjoint sets. So when there is not any common element, when there is not any common element, then it is called as disjoint sets. So I'll write like this: A equal to A comma B and B equal to C comma D. So we can see that there are two sets, A comma B, A and B. Both does not have any common element here. So what is disjoint set? A disjoint set is A intersection B, which results in pi here. So we are not able to find any common elements here. So these two are called as disjoint sets. So we'll be discussing about functions. A function associates input value to a unique output value. For example, a function can be denoted mathematically like this: f of x1 denoted to x2. So this is the way how a function is mathematically associated. Suppose I have a relation is equal to 1 comma 2 and 3 comma 4 and 2 comma 1. So now I have this first parameter is called as x values here. That means it has to be in the relation called as set called as x1. So in the first set I have 1, 2 and 3, and when you take up the second one we have 2, 4 and 1. So I rate it as 1, 2 and 4. So this is called as x1 and this is called as x2. So when you draw it, so 1 is associated with 2 and 3 is associated with 4 and 2 is associated with 1. So since every value of x in x1 is mapping with x2 over here. If this is the case, now this is called as anything which is in x1 is called as domain and anything which is in x2 is called as range here. If x1 matches with x2, then we can say that if every value of x1 matches with x2, then we can say it is called as a total function. So we can say it is called as a total function. So in this case, we can say it is called as a total function. Suppose we have another value. Say for example, I have a relation r equal to 1, 2 and 2, 3, and in a set of elements are 1, 2, 3. So these are the set of elements. Now when I write like this, so x elements are 1 and 2 and y elements are 1, 2 and 3. X elements are 1, 2 and 3. Since you have in A you have 3 elements and in Y you have 2 and 3. So 1 maps with 2 and 2 maps with 3. But it is left alone. 3 is left alone in x1. x1 this is called as x1 and this is called as x2, and x1 is called as domain and x2 is called as range. So in 3 is actually missing. It does not map with any output value in x2. So if this is the case, it is called as partial function. That means if some values in domain, does not map with range, then it is called as a partial function. So in this case 3 does not map with any other values in range, so it is called as a partial function here. Now we'll concentrate on what is meant by relations. So relations, there are t types. One is called as reflexive. Number 2 is called as symmetric. And number 3, it is transitive. So when you can say a relation is called as reflexive, say for example, we can say a relation is called as reflexive if you assume like this, reflexive. So this is meant by reflexive. Let us assume that A is equal to 1, 2. So we can say that for all A belongs to relation, so we can say that there are 2 elements 1 and 2, then it implies that A, belongs to relation. So if this is the case, so for all A belongs to relation, then you can write A belongs to relation. That means for every element in the set A, you should have the corresponding match over there. That means in this case, I can say that this is called as a reflexive relation when you write R is equal to 1, 1. So 1 is one element, so A, and 2 is another element, you can write 2, 2. So this is called as reflexive relation. So if I write like this, A equal to 1, A, B, C. So when I can say this is called as reflexive, so I can say that R equal to, if I write A, and then if I write B, and if I write C, so we can say that this is reflexive. So if any one is missing here, though, we cannot say that this is reflexive. For example, I have a set. For example, I have a set A equal to 2, 3. So if I have a relation R equal to 3, 3, I cannot say this is reflexive because there are two elements 2 and 3. We have only 3, 3. The definition says for all the elements, but 2 is missing here since 2, 2 does not belong to relation. So it is not reflexive. 2, 2 does not belong to relation, so it is not reflexive. Now we'll go for the next one. The next is called as symmetric. So symmetric, so I can say that for symmetric, the condition is if A comma B belongs to relation R, that implies B comma A also belongs to R, then it is called as symmetric. So let us assume that I have a set called as 1, 2, 3. Okay, and I have a relation R equal to 1, 2, and I have the relation called as 1, 3. But I cannot say that this is a symmetric relation because I have 1, 2. What the condition says, if there is A comma B, then obviously you should have an equivalent pair for this. If 1, 2 exists, then obviously you should have 2, 1. And if 1, 3 exists, obviously you should have 3, 1. If these two cases exist, then it is called as symmetric relations. Now, suppose I have a relation for the same set 2, 3. So, since the relation have 2, 3, but 3, 2 does not exist over here. So, 3, 2 does not belong to relation. So it is not symmetric. So we can say that this is not symmetric. Now we'll go for what is meant by transitive here. So what is transitive? So transitive, if A comma B belongs to relation and B comma C belongs to relation, so which implies A comma C also belongs to relation, is what it says. Let us assume that I have 1, 2. Now I have a relation like this 1, 2, and whenever I say transitive, you have to start with whether anything which starts with 2, anything which is going to start with 2 exists. So suppose I have 2, 1. Okay, these are the two relations. Now whether transitive dependency exists over here. So 1, 2. So 1 is A and 2 is B. Now you have to identify whether any relation starts with B. B is here too. So again it starts with B called as 2 and C is again 1 here. So this is B and this is C and this is A and this is B. So it starts with, but whether this is transitive relation, no, this is not called as transitive relation. What is transitive relation? If A comma C exists, so what is A? 1, and what is C? Again 1. So if I write 1, 1, then I can say this is called as transitive relation. Okay. then we can say a relation is an equivalence relation. So we can say a relation is called as equivalence relation when it is reflexive, when it is symmetric, when it is transitive. When it is transitive, we can say this is called as equivalence relation. So what is the example for this? Let us assume that a equal to 1 comma 2. Okay, now I can say that whether the relation is reflexive or transitive or symmetric, I can write like this. So 1 comma 1 exists, 2 comma 2 exists. Okay, now and I can write like this 1 comma 2. Okay, and if I write 2 comma 1, okay, now I can say that this relation is symmetric, reflexive and transitive. So how will you say it is symmetric, reflexive and transitive? Let us check for reflexive. How many elements are there? 1 and 2 are the elements. So 1 comma 1 and 2 comma 2 exists. So this is reflexive. Whether symmetric. Now listen here, 1 comma 1. So if you just reverse it, you will also get 1 comma 1 that exists. 2 comma 2. If you reverse it, you will also get 2 comma 2. But 1 comma 2, when you reverse it, that means alternative pair 2 comma 1 exists. So for all the pairs it exists, for it is called as symmetric. But what is meant by transitive? Now listen here. You take up the first pair, A, this is called as A and this is called as B. Okay. And whether anything starts in 1 here, yes, 1. So this is called as B and this is called as C. Okay. If this relation exists, whether A comma C exists, A is 1 and C is 2. So 1 comma 2 exists. So obviously 1 comma 2 exists. So this is called as a transitive relation. Now you come for the next one, whether 2 comma 2 exists. Yes, this is A, this is B. Now whether any relation starts with 2, yes, 2 starts here. So this is B and this is C. Whether 2 comma 1 exists, yes, A and C exist. So 2 comma 1 exists. So this is transitive. Now I take up this relation 1 comma 2. So now I write this as A, this as B, and this as B, this as C. Now A comma B, 1 comma 2 exists. B, it starts with 2. B comma C, 2 comma 1 exists. Whether A comma C exists, 1 comma 1 exists, yes, 1 comma 1 exists over here. So this is an equivalence relation since all the transitions are getting fulfilled. So this is called as an equivalence relation. Now there are two types of proof, mathematical proofs. So mathematical proofs, first method is proof by induction. And second is proof by contradiction. I can say that what is proof by induction? So prove 1 plus 2 plus 3 plus up to n is equal to n into n plus 1 by 2. So we can say that first check the basis condition. So basis, you assign n equal to 1. So you have to prove that left side is equal to right side. LHS equal to RHS. When you write prove n equal to 1, apply n equal to 1, n equal to 1, and when you apply n equal to 1 on the right side, 1 plus 1 divided by 2 is equal to 1 is equal to 1. Hence it is true. Now you apply for induction step. Induction. So induction n equal to k. Now you rewrite the equation. So substitute k instead of n here. So 1 plus 2 plus 3 plus n is substituted as k is equal to k plus 1 divided by 2. Now this is step number 2. And the third step, you have to substitute n equal to k plus 1. So what is the original equation? So 1 plus 2 plus 3 plus. Now when you substitute n equal to k plus 1, obviously the before value before that is called as k is equal to. Now when you substitute n equal to k plus 1, so k plus 1, now n is replaced as k plus 1 plus 1 and divided by 2. So rewrite this. When you rewrite this portion is substituted by this formula. That means k equal to k plus 1 by 2. So I substitute here k equal to k plus 1 by 2 plus k plus 1 is equal to, now we can rewrite this, k plus 1, k plus 2 and divided by 2. So now when you rewrite this, so we can multiply this 2. So k plus 1 divided by 2 plus 2k. You can write 2k plus 1 divided by 2, and when I rewrite this, it becomes k squared plus 2k plus k plus 2 divided by 2. And when you simplify this becomes k squared plus k, now 2k plus 2 and divided by 2. Here it is k squared plus 2k plus k plus 2. So when you see here, the LHS equal to RHS, so everything you can cancel it. So you can say that LHS equal to RHS. So hence this is called as a proof by induction method. So proof by contradiction is you assume a hypothesis, something is false, and then you try to prove that it is true. Or you assume that something is true, then you try to prove that it is false. So this is called as proof by contradiction. So I will prove root 2 is irrational. So irrational in the sense that you cannot get a fraction value. Okay. So root 2, you have to prove that it is irrational. So you first assume. So you assume root 2 is rational. Assume that root 2 is rational. So if you make that root 2 is not rational, so I make like this, root 2 is equal to, I write like this, a by b. So rational number is anything which is written in fractions is called as rational number. So when you find a square this, when you square this, you will get root 2 becomes 2 is equal to a squared and b squared. So now cross multiply this. So 2b squared is equal to a squared. Okay. Now when you multiply any number with the square of a number, always it is even. So when this is even, this should also be even. So a squared is even, whereas 2b squared put together is also called as even. Now what you have to do is assume that a equal to 2k. Assume that a equal to 2k. So when you multiply this, assume that a equal to 2k, so this will become 2b squared and a squared will become 4k squared, and you substitute it. So this 4 squared k squared can be written as 2b squared is equal to 2.2 k squared, 2.2 k squared. So anything which is on the multiple of 2, we can say common factor is 2 here. So here also 2b squared is equivalent to 2k squared. Anything which is in the common factor of 2 can be considered as a non-fraction number. That means we can say that this is irrational. So initially we assume that it is rational. Now we prove that this is irrational. So factor of 2 is a rational number. So thanks for watching the video. Have a good day.